So, well, first of all, I want to thank you for actually extending the invitation to present here. It's very kind, and I hope that what we're gonna do today gives you a better, grasp of what W is, because somehow it's a tricky kind of thing. And I saw when Natalia was explaining again transition to work, it's kind of natural to think, you are doing the transition, so it will detect transition faults. But these things get a bit tricky. And so I believe that the best way actually for you to get the real grasp of it is actually doing something. It's actually testing real implementations and everything. So yeah, I see even the slides. I've been sure they will be quite useful. And so we will try exactly, I have prepared some resources. There is some form of a simulation of this PAP protocol that we'll be playing with. And we will be trying to detect an actual fault in real software implementation of PAP. Of course, with all these methods that Natalia just actually described. One thing that I want to mention and insist on that Natalia was saying is that, sure, it's kind of hard to model anything with such restrictions. You need a machine which is complete, deterministic, connected, initialized, etc. And so it is difficult, but if talking from a testability point of view, it actually gives you more advantages if you manage to design, for example, your protocols like that, rather than if you're not, because you can guarantee some things about your implementations, exactly. So this is also a matter of design and enforcing this type of design, in fact. So, well, my name is actually Jorge. So for everybody that speaks Russian here, that shouldn't be a problem. For those who speak, other languages that didn't have this ha sound, George, it's completely fine. So let's move on to W. So we saw how W, the main idea of W is exactly in this part. As you can see in all this area in there, this is sort of the transfer sequence part, right? So this is where we were saying, okay, from the initial state, we will reach each of the states of the implementation, well, of the specification, or when you're testing it of the implementation, through a sequence. And this, they have different names. I like to call them transfer sequence. I guess that this, Natalia was calling them state cover set, but it's the same. It's just to reach from the initial state to each of the states. So these are, of course, complete and deterministic FSMs and connected, of course. They always exist, and you can always, of course, reach from the initial state to any of the other states. And they're pretty simple to derive, in fact. So let's start by warming up. I guess that you already have much more experience than this, but what would you say, how would you reach in this PAP protocol? How would you reach the state try 3? What would be the sequence that you can do it? Let me see if I can see the chat, because I don't see it. And I see it now. Yeah, okay. You want me to maybe put the machine? Yeah, maybe that would be useful, right? All right. Let's see, I have it here. So yeah, I have it there. Who can tell me how from the initial state, what is the transfer sequence that will make me reach for a fact try 3? Sometimes in this Zoom, I don't know if I'm speaking to myself or not. No one? Okay. So let me start. We will say that this transfer sequence for try 3, it's simply, if you want to go and you want to reach try 2, and then you want to go and reach try 3, as you can see, you need to apply rar minus and rar minus in here, right? Okay, so so this will be rar minus, rar minus. This is the transfer sequence to try 3. And so you can have, of course, different transfer sequence to reach the states, but I will focus in here in the shortest transfer sequence, right? Because it's easier. So what would be the transfer sequence to reach the state open? So, that's perfect, of course. So that's a very simple one. This is rar plus. So let's go back to where we were. So as you can see, this cover set V, this is exactly all the sequences that you have to reach each of the states in the FSM, right? Now, what do you do? What is it, right? Like this test suite 1, and what we were saying is like you reach each of the states, and then after reaching each of the states, you apply W. So the W, set, it's somewhat long in here. It has I guess around 10 sequences, we were saying, something like that. And this is exactly to distinguish each of the state pairs, right? So for example, let's say that we reached, the state open. So this is rar plus, and then you need to distinguish this state rar plus, I mean, that you reached with rar plus from each of the other states, right? So then you will actually append in there all the sequences that are these distinguishing sequences that you had before derived, right? So you will have, for example, as you can see, if you have the slides of Natalia in there to distinguish ACK and open, you will have rar minus, rar minus, rar minus, and then rar plus. So this is one sequence that belongs to W, but then you need to have all the others as well. So you have rar plus, and then you need to distinguish, exactly if this is the state, for example, open or try to. But since you don't know which state you actually reached, you need to try them all, sadly. Well, Natalia was also telling you some insights of how to, of course, reduce this test set. So you will, try some other things like, one by one. And so you append them. And you have to do this for each of the actually states that you reach. Now, this can be, not that simple to remember or, to grab a hold of. But the best strategy to do that is to actually construct a tree. So you sort of simulate the behavior of the FSM starting from the initial state, of course, assuming that this is an initialized machine. And so this is something that I wanted to have very, very clear before, we start doing, everything with implementation. An easy way to remember W is the following: you reach, distinguish, whatever you reach, you distinguish it from the others. And also you need to traverse all the possible inputs. And this is the second part, right? This is the part that we're talking here. And then you need to distinguish. So as you can see, once you reach the state, we were talking about appending, the W set in there. But also you need to execute all the possible inputs, of course. And then after you reach another state, you need to append the W set. So that can be quite long. And this is what I propose to you that we will start doing. But first, let's start, getting some, kind of touching for the code. So if you can go to the code that I've created for you in there, I'm gonna tell you something before you download it. This code was created in very few time, and so don't blame me. I know that there is a lot of things that you can improve on that, and you're welcome if you want to improve it. Please do. But it's just for you to get an idea, okay? So why don't you go ahead and download the code from there? You can have a QR code or the link in there as you prefer, and let me know once you have it. I do not know if you can clone the repository. I believe that you won't have the rights, but you can download the code real quick. So yeah, it's exactly on this on the repo. You have this kind of down arrow. So let me know if you're having troubles or if you meant to actually download it. In this repository, I included already pre-compiled versions for Linux and Mac OS X. If you are not running a Linux or Mac OS X, I will sincerely apologize, and I hope that you do have a C compiler. But it's a matter of simply compiling this pap.c program, right? Please do let me know when you're downloading and how is it going. Okay, yeah, I for Mac OS X, I think there is no problem because me myself, I did it on Mac OS X. Yeah, I can write in the chat for sure. Yeah, okay. So it's here. Once again, yeah, Fedora, nice. I actually compiled it on an Ubuntu, and I thought since it doesn't have many weird libraries on it, it should work on any Linux. Well, I don't know if you compiled. Maybe you compiled as well. That can happen. Okay, so let me share for a second in here my terminal. So for those of you who already downloaded it, or well, people that are still downloading, but of course the repo contains a couple of files. The important ones are either the main code, and you can have this code in here, and it's a very naive implementation. I want to talk real quick over how was my idea of how to implement this state machine, because being honest, when people they code things, they don't always think like, you know what, let's code it like if you're in this state and you have this input, let's apply this, and so on. So what I did is a very simple logic. So basically, you have a number of tries, which is a variable. I assigned an integer. I know it's way too big for assigning 3 values. That's okay. A char would have been enough, but it's an unsigned integer, and also I have a variable for either if you have been successful or not. Once you're successful, you can stay in the state of being successful forever, and that will be perfectly fine. Right? So it's very simple. If you have, a bad input, then and you have less than 3 tries, you just output it's bad, and you increase the number of tries. If you have a good input, you make sure that success is on, and if it's a bad input, there's a lot of tries that you've done, so you're a bad guy and you're banned forever. So it's a pretty simple logic. And how it's done, it's actually checking some login for user and password. So if you go to this file, which is called users.db, you have the actually valid user and password combinations. You can add in there, of course. I added some, by default. And then I felt so egocentric that I was like, maybe I should add something different, but I don't know what to add. So it's complicated. So you can add, valid user and passwords just separated by a simple space in there. And once you do that, you can try the implementation. You would try the implementation. Let's compile it real quick. Well, I had already the binary in there, but doesn't matter. So if you execute it, you will see that it asks for the user. So you will put some user and then some password. So I don't know, something like that. So you would see that the reaction of the program is actually to say, okay, so the input was a rar minus, which is a wrong, input. And actually the output for this that you provided, it's san, which is not an act or something like that. And so, of course, if you provide a good user and password combination, it will actually reply properly and so on. So if that's something also very important, if you want to quit the program, I didn't do anything fancy. So you just do a Control-C and that will get out from the program. So whenever you're trying to do a reset sequence, that's just quitting the program. And that's about it. Now, why don't you go ahead and really just try whatever that this binary, could you zoom the terribly sorry, yeah, sure, you don't see anything. Yeah, all right, what about that? Is it better? Cool. All right, sorry, my bad. I see my screen and I can read perfectly. So I forget sometimes. So yeah, I was telling you that you can just go ahead and just hit in there your user password combinations, and if not, you do a Control-C. So please try to check and try some test sequences and tell me honestly, do you see the bug in the program? I mean, there is, and this is a fact, there is for a fact a bug in the program, but it's kind of hard to see which bug that would be. So I'm going to give you some minutes so that you can touch it, play a bit around with it, and then we will see how you feel about it. Should it stop after 3 failed attempts? No. We were trying to replicate exactly the behavior of the machine being complete. So after you're in one state and you apply another input, it still accepts it. Right? After logging in, it doesn't stay unopened. Ah, it should. It should. Let's try. So let's say that I actually logged in. So is it in the open state? I would say so. And how can I know that this is in the open state? Well, because I can forever with many bad passwords, but once I hit a good one, it tells me, it's the good password. And this you can see in the FSM specification, right? Also, I mean, at the side in the code, you can also see that once the flag is marked as success, it's successful, and that's it. Doesn't matter what else happens in life. Once you're open, right? So yeah, it stays in there. In fact, and this is something interesting because you will test it with W right now. How do you know that? How do you know that actually you are in the open state and not in other state? You will distinguish it exactly via the W set, right? But we will move on step by step. So is it supposed to print rar plus sun? Rar plus and sun, it would be yeah, it trims the spaces. Yeah, it trims. I think that I did a trim, in my opinion. So yeah, that should be fine. Also, it's supposed to a plus with sun. I guess it's part of the specification, the state closed. Yeah. So that means that you're in the state close. So let's just, I'm trying to convince you that my implementation is correct, even if I'm telling you it's incorrect, right? So one bad attempt, one good attempt, it seems like it's in the open state, right? It seems like it is in the open state. Okay. One bad attempt, the other bad attempt, the third bad attempt, and then a good one. It is in fact in the closed state. All right. Let's try 2 times. So a bad attempt, another one, and then a good one. It's in the open one. So me, I would say that kind of works, and I would strongly believe that, someone great coded that program. But in fact, sadly, this is not the case. And just for you to start getting familiar with, and this is going to be a part that you might find it horrible, but why don't you derive a couple of tests? You can either let me start sharing the other thing. Where is it? It's here. Yeah. So why don't you start deriving, for instance, a transition tool and applying it to this implementation, right? So, for example, a transition tour, would be something like rar minus, right? But let's try to cover. Let's try to cover here, for example, then here, and then these 2 transitions. All right. So you can do that with a single, go, and that will be like rar minus, rar plus, rar minus, rar plus, right? So we would have covered this one. Well, let's do it like that. Let's do it like this. This is covered, and these 2 are covered as well. Okay. Then there is another sequence that it's just rar plus, in here, And then if I want to cover, for example, these two, I will do something like var minus, var minus, and then a var plus, and I will cover these other two, right? And then finally, to cover the others, I will do something like I don't know, var minus, var minus, var minus, so var minus, and then I'll do var plus, var minus, something like that. So if I execute these kind of sequences, let's see if I can detect the bug. It might detect it actually. I modified something today. Let's see. So actually, it did detect the bug on my implementation because I changed something today. This is not fun. But let me do the one that it's good. So I said minus, 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 minus 3 times, and then, yeah, that's okay. So as you can see, the expected output of the last sequence, yeah, it's correct, right? So if we go to the to checking all of that, the program actually detected did not detect, sorry, the bug in here. Okay, and there is a problem that I modified the code today because I thought I was very clever, but it's actually not working. I broke the code in a different way. So the executables, they're fine. The code, I'm very sorry, I will update it. It's very soon. Now, this is, for example, the transition tour method, and you can try it yourself. Now, what is the test suite that you will be deriving using W? And tell me if it detects the fault, of course. This is a very long test suite, and so we can sort of start building it together, right? So we were saying already that to reach, each of the states in implementation, we would have this transfer set. Okay, so can someone tell me, for example, one sequence that reaches the state try 3, and then a couple of sequences attached to W? How would you actually go about that? So we can start creating sequences. Let's do it like this. Let's do like that. Let's say, okay, try 3 I can reach with var minus, right? Very simple. And then I start attaching, W. And I will just copy paste from what I have here. So this is one sequence. And then, of course, if I reach try 3 again, with var minus, and then, I actually keep copying the W set. This is another sequence that it's in W, right? And so on and so forth. So that's gonna be quite an extensive, test suite that you will have. So can you please, try to derive this W and try to apply it against this, running software that you have, and tell me, normally I wish I could be, face to face with you. I usually give some gifts at least some candy, for the people that they are the first of actually finding the bug. But now I cannot give you candy, so and I'm not gonna transfer you Bitcoin, so there is no price today. So if you can only tell me what is the sequence that will detect the bug in the program, that would be great. So I'm gonna give you some time. Tell me if you have any troubles either deriving W or applying it to the implementation. Just let me know.
I have two questions.
Yes, please.
So the first one, I'm not sure if I understood that correctly. The executable that was in the repository is fine, but the source code is, we should not use that. The executable produced on that one, or?
Yeah.
Okay.
I made a how to tell you? I thought it was too obvious where the bug was, so I made it less obvious today. I was like, come on, these people, they're smart. Let's give them. Yeah, I'm sorry.
Okay.
I'm sorry. This is
No,
the
no.
late minute kind of modification that I thought I would do, and I'm like, come on, they will see. But then when I modified that, it became slightly easier to detect the bug. Okay. Why? And this is what Natalia was telling you. Sometimes for certain transition faults, even a transition tool is able to detect this bug. So my apologies once again. While we're talking, I'm gonna try to fix it. Let's see if I can. You will see my panic eyes while coding, back what it was. Sorry, I need to make some tea. That's very important. Are you trying to find the bug? No, 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 no. I mean, sure, we are all trying to find the bug, and the goal is exactly derive the W test suite and you know try to apply it to the program. Now, if you download the program once again, I updated the repo, by the way, and now you have the correct code. So let's pretend that this never happened. But still, you need to sort of find the bug either in the code. The binaries, they stay the same. The binaries they were always correct. It's just if you were compiling the code, you would have a different thing. Now the code corresponds to the binaries, so anything is fine, either with the binaries or with the code. You need to find the bug. You can apply any method that you wish. Just tell me what's the sequence. My proposal is exactly that. You derive W for obtaining all the sequences possible to actually detect the bug and to show you how W is useful, right? But you can make some tea. I'm all up for tea. I'm up for coffee as well. So go ahead and you keep trying. You can have your tea and coffee, and you can continue trying to find the bug.
I think I found it, but like I have to admit, I never did this work with like finite state machines much, so I have no idea how to use this W method. So I tried to just look at the source code.
All right. So you
I
found the bug in
maybe and like just
yeah. Okay. Now this is what we were saying exactly. It depends if you consider that this is black box or white box testing. If you don't have access to the code, you don't know, exactly if the code is correct or not, etc. W, exactly, this is the point. You don't need to know how it was coded, who did it, why. You have one binary, and you can test it, and you can say, yes, this binary is actually good, or this binary is actually having a bug, right? Well, of course, when we're saying that we are limiting ourselves, of course, with certain types of bugs and under certain constraints, as Natalia was explaining. But yeah, for this is an FSM model, and then you're saying, yeah, this is free of transition and output faults. So yeah, no, don't spoil it so far. Just tell me if you have troubles constructing W, because this is exactly what I want you to be able to do today, to actually be confident that you can construct W, right? And probably apply it to real software someday, tomorrow, today, of course. So let's do a real quick poll. Who in here is deriving W or is having troubles deriving W? Let's start with, is there anyone having troubles? Like, if there is someone, can you tell me what's that you actually don't get, or that you would feel that, or you're completely lost, or how is it going? You don't know where to start. That's a very valid thing, and I would say that the best way to start is by the root. You remember when we were saying that this can be done like a tree, right? Let's go back to the slides in here. This can be done like a tree. So you start in the initial state, and then you move to all other states, and then after all other states, you start appending the sequences. So For our case in here, you would start with ACK, and then you would move to, with rar minus. So this is kind of a tree structure, right? That you're going down. First, you start with ACK, and then you apply all possible inputs. In here, this is a binary machine, so it will be a binary tree. With rar minus, you will go to try to, and with rar plus, you will go to open. So you have reached, in fact, you have reached actually 2 states, right? So first, we said, let's go and transfer to all of the possible states. So in here, then after try 2, you will have another tree. And let me see if I can kind of write it down real quick how I would do it in here. And then after actually reaching try 3, you can reach the state which is called close, right? So yeah, it will be something like this. You will have to forgive my handwriting in here. So I was not prepared for that, but as you can see in here, you start, with ACK, and then you go with minus, and you will start to this state, which is try 2. And if you go to minus, you will go to the state close. And if you will go with minus, sorry, where am I? No, you will go to the state 3, sorry, in here, try 3. On the other hand, if you're in the initial state and you will go with plus, then you will go to the state open, right? So this is the beginning. You will go to all of the possible, let's say, states that you can reach from the initial state. And then after you actually reach each of these nodes, in there you have to add, for example, let me put it back in here. So you will add W, let's say in open, you will add W. And what is W? You remember, these are all the sequences that they are distinguishing all the state pairs, right? So this is this distinguishability set. So in here, you will add, I don't recall precisely the sequences, but let's say that you have 10 of them. And so you will attach to this node the minus, minus, minus. And so this is how you create it. This is one possible way to create it as a tree. Now, if the view of a tree is not that convenient to you, it's nice because you don't repeat sequences, right? But you can also do it without knowing the tree, let's say. And it's exactly as explained in this slide in here. So first you will reach some state, and then you will add the sequences that they're distinguishing, and you will append them, right? So for example, to reach the state try 2, you put a rar minus. And then after a rar minus, all the sequences you attach. So the sequences, you remember that we had 10 of them, and let me copy them to you real quick. So these are all the sequences to distinguish, right?
So then is the goal to write like a script that automatically goes through all the states, or like produces them, or are we supposed to like just try out the states in order to find out when there's like a faulty transition?
Exactly. So the construction of W, if you want to make it automatically, of course, this is somewhat complicated because you need a program that would read a finite state machine, and then it would go exactly doing all these kind of operations. But I was thinking of you doing it manually, right? So these are all the interesting. Okay, so these are all the distinguishing sequences for each of the state pairs, right? So let's say that I'm reaching now state try 2. So to reach try 2, we know that this is rar minus, and then I will append each of the sequences that I just sent to, in fact, rar minus. So that way, I am attaching the W set, to the reaching of this state. This example, for example, when we, assuming that this state in here would be try 2, I need to attach all the sequences of W here. So that's the main idea. So there is a lot of sequences that you will have, and some of that sequence will actually be able to detect the fault. So I have a suggestion, I guess, of what's the sequence, and this comes from Nikolai. Let's see if Nikolai is right. Minus 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 plus plus. Let's check it out. Let's check it out. I'm gonna share real quick my other screen. That. Yeah. Okay. So this is the proposed sequence. So let's try it out. So minus 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 plus plus, and that is correct. This is a sequence that actually detects the bug. Why? Okay, let's go. And if you see the expected output reaction of the specification, after 3 tries, whatever, even if you're outputting the correct user, actually, you will always reply sun, right? You see it in the specification machine, right? But you see that the implementation, actually, when you actually execute this sequence, is not replying the same. That means there is a fault. That means there's a bug, and we found it through this sequence. Now, can I ask Nikolai, how did you find that sequence? Tell me, did you apply W, or did you just wild it, like trying many things? Maybe he went for doing some tea, I guess. It was I see. So Nikolai says that he just got inspired, something inspired him. But this is this is good that you were inspired. Now the thing is that if you want to once again go with W, there's a lot of sequences of W. I know everybody should be hating this, right? So let's for the sake of trying to make you understand this W, let's try exactly deriving one piece of W. So we said that these are all the sequences that we have in there, right? So what I'm going to do is that these sequences, I will kind of cut the preambles. Let me see. Okay. So let's say that I want to start deriving W. So first I need to reach one state. Let's say for the sake of something that this is the state try to, which I will reach through rar minus, right? So all the sequences that I need, in fact, to distinguish all the different pairs of states are those. So the sequences that will go actually to W is actually, the concatenation of the transfer sequence, which is rar minus, with all of these sequences in here. So that will be nothing more than, actually adding rar minus at the beginning of everything. So in fact, so by adding the transfer sequence to try to the W set, you get this. Okay. So you see, the W set is the distinguishability set. This is this set that helps you distinguish, am I in the right state or not, right? It helps you distinguish between all state pairs. So this is, first traversing, in fact, this part, right? So you actually, let's just remove stuff for the moment. So this is, in fact, what I placed in the chat. It's exactly, first I traversed, I reached try to, and then I added W to try to. Okay. Now, this is W. It's all these 10 sequences that we have in there. Now, if you want to do the same, but let's say in the other direction, if you want to do the same to open, and then adding W, what are the sequences that you think that you will have to add to the test suite in general? Can someone tell me? So how do you transfer to open to begin with from the initial state? RAR plus at the beginning. That is perfectly correct. So you see, you're getting exactly how to do it. So RAR plus at the beginning, and then I attached all the distinguishability set, W, to it. So that will be, in fact, all the test sequences which I'm about to paste. Which are these sequences, okay? So now the same goes. If I go for try 3, this would be exactly first to transfer to try 3, which is RAR minus, and then appending to this all of the sequences for W, right? So that's a huge work, and I admit it. Now, this is in fact easy to see the why using a tree is better, because as you can see, there are many repeated sequences that will be, sort of merged into a single one. But if you want to use the tree and you just want to, do transfer sequence W go, that's perfectly fine. That's absolutely fine. You will have just some repeated sequences. You need to sort unique sequences, and that'll be it. Now there is another part for W. So the other part of W, it's in fact, you actually reach the state. For each of the inputs, you execute this transition, and then you add the distinguishability set, okay? So let's assume that we're talking about try 2. So for try 2, we said that it was RAR minus to reach, then RAR minus one of the possible inputs, and then all the sequences that they are in the distinguishability set, right? So RAR minus, RAR plus, I'm going to put it W, right? Also, you reach try 2, you do the other input, and then you add W. So you will have all these sequences to actually generate W. And of course, this is the second part. This is this second test suite that we were saying here. This is the second part, and actually when you combine both of them, that's the final test suite that you need to apply to create W. So let's see. The idea, once again, is, I reach the state, I execute the transition, and I distinguish. Am I in the right place? Am I not in the right place? Right. That's the whole, thought and idea of W. Now, if I ask you a question, can you tell me, the sequences that will be necessary, for example, to check the state try 3, and then with the executing the input rar plus. How would you go about that? Okay, let's make it simpler. How would you reach try 3 from the initial state?
R minus R minus.
That's correct. So after you have rar minus, the sequences, if you want to execute the transition with rar plus, that will be in fact doing a rar minus, and then a rar plus, right? And after executing this transition, we need, to append that to, this preamble, we need to append all our distinguishability set, right? So the sequences that will go on W are all of this that I'm about to paste here, right? As you can see, all of them, they will have the same preamble, because this is in fact reaching try 3, executing the transition with the input rar plus, and then attaching all the distinguishability set to it, right? So
I understand the W part and the going there part, but what is the purpose of throwing in one transition in between? I didn't understand that.
Okay. So basically trying one transition in between, and this is why W has 2 parts, right? So the first part is you reach the state, and then you say, I want to distinguish this state from the other, right? So this is the first test suite that you're doing, or the first part. The second part is, okay, I reached the state, and now I want to execute this transition, because maybe it's in this transition that there is a fault. Once I execute this transition, I need to distinguish between, the states. And exactly the idea is, once I executed the transition, if I'm in the correct state, all the outputs will be the same. But if you are in another state, you will have some difference. That's the main purpose of the second part of the test suite.
Okay,
And
I think I get it now. Thank you for your patience.
No, but there is, this is what we're here for. And exactly, I think that W is so tricky, even if it sounds simple, that if you don't try to do it, or you don't try to play with it, it's not understandable, even if it sounds simple. So don't worry, it's not about you, it's everybody. We had all the same troubles, I think, understanding W. Okay, but someone out of divine inspiration actually came up with the sequence. Well, all right, I'm going to tell you that W actually guarantees this actually detection of it. Now, if you know how to, actually how to derive W, and you have the intuition behind W, I'm going to tell you that in the program, the transition that it's faulty is this one. Okay, so if you recall correctly, this was the case that in close it will stay here, but in fact, rar plus actually goes there. Now, if you know this transition, this is the fault that actually it's responsible for this. Sorry, so this is the exact fault that it's in the implementation. Can anyone tell me what is the test case that you will use to detect this specific fault? Daniel, has a very interesting question. What if I add some sort of non-deterministic behavior to the implementation? Is the question. Well, to reply to that, we assume that, of course, both the implementation and the specification, they're deterministic. This is something as well that we were saying how restricted we are, right? Yeah, unpredictable, we will say it in the sense that under the same input, you can have different output reactions, right? In reality, this is often encountered even yeah, with options, right? So for example, it depends on your level of abstraction, but you could say the same input is the same username, and then the different input is the password, and you can have, depending on which good or bad user you take, this is also different functionality. So this is, of course, non-deterministic behavior. So yeah, this is not the case for the moment. Anyhow, so who can tell me? Come on, what's the intuition? How can I detect this fault that it's in here? I know that you have it. You're probably just shy to say it. How can I detect that fault? I know the fault.
Since no one is answering again, I would suggest we go to the state before the faulty transition, and then we apply it, and then we append W, and then check for the output.
That's perfect. That's perfect. I go to the state close, I execute the transition, and then I do double. That's it. Now there is a slightly better approach to this, because you know in which state you are in the wrong transition, right? So you don't need all W, because you know where you are. So you need just to distinguish between ACK and close, because you should be in close and you're in ACK, right? Did you get that? So you don't need the whole, W set, because you know for a fact that now you are in one state. So you just need to distinguish between these two states.
I mean, maybe to be sure that no other bugs were introduced.
Yeah, no, exactly. But this is a good, you have the right spirit, and this is the only spirit that you should have. In fact, well, testing, a software, a new one with guarantees. The only way to guarantee everything is to properly apply W, right? That's it. And W will detect your fault. If, once again, we're considering output and transfer faults. Yeah. Now, the sequence that you will get to detect this fault, in fact, it's the sequence that, who was it? Nikolai gave to us, in fact. You see? How do you reach the state close? It's 3 times var minus, then you execute the transition var plus, and to distinguish between ACK and close, you need RAR plus. So this is the precise sequence that actually Nikolai gave us, And so this is the precise sequence that detects the fault, So let's move on a bit because we don't have that much time now left, I suppose. I know everybody says the same, and imagine that I have 30 states, or let's not say 30, 15. That's okay. That's a regular machine, 7, 8. I have to do this for each of the inputs. What if I have 10 inputs? I will not be able to actually do it with my hands. My brain will go nuts. I will go crazy. And this is true. I would go crazy myself as well. Now, there are some tools that they have been recently, well, now not that recently, but for a couple of years. They are open to the public, which is super good because before there were some tools, but they were, not that shared, let's say. And I'm gonna speak about one in there, and I'm gonna just kind of copy paste in here probably the link to you all. And this is this tool. I have to say that this tool was developed by by the group of Professor Nina Yevtushenko. She's actually part of HSE, so some of you might already know her, and if not, probably you will get to know her at some point. And so the tool is very useful and it's very nice because it has a simple web interface where you can submit your FSMs and it will derive actually, test cases for you. So there are a couple of things to know, when you're using these kind of tools. There are a couple of things. Either there are some formats which you will have to encode, your states. Instead of try2, you will put this as a number 1, and instead of ACK, you will put as a number 0, and so on. Or sometimes, if not, you need to list explicitly the states. Okay. So to learn about the FSM file format, which is the file format that most of these tools they take, you have a couple of resources in there. If you go to the example section of this link that I actually told you, they have a very good explanation in there of everything. If not, I also have some explanation, but there is a problem. Notice that sometimes we disagree on the order, of the transitions, because the transitions are described like state input, output, next state, or vice versa, state input, next state, and output. So that's a bit of a tricky thing in there. Yeah, so some explanations you will find here, and also in the example ones, you can check them out. So why don't you go ahead and try to use this service? You create your own PAP machine, and then we will see the test cases that it generates. I will give you a couple of minutes in here as well, and then after that, I will do it myself to show you more or less how it works. Of course, if you have any questions or everything, I'm here, or in the chat, or in both places. Is someone talking? No. We are. I hope not.
Hi, Bertrand. We're finishing the previous lecture, so yours is starting in 20 minutes.
Okay, so I'm not missing anything.
No.
Okay.
Sorry, sorry, Jorge.
Don't worry. Don't worry.
Okay.
So anyhow, this, I don't know if you are already in this tool. I'm gonna paste an example of an Fsm file. This is kind of what you do in there. So you can sort of start modifying this file to reflect more PAP protocol, or well, you can start from scratch as you wish. Anything is fine. Sorry. You just need to modify. Of course, we have 5 states instead of 4, and the list of the states is different. But yeah, please go ahead and let me know if you can see the site and how is it going. Correct. That text is the format for an FSM file. And so you need to do something similar, but for the PAP protocol, it shouldn't be that different. So we'll give you a couple more minutes, and then since I guess our talk finishes also in 8 minutes. Then I will show you the file and, of course, the generated test suite by W from the tool. Let me see if it's correct or not. Okay, just real quick, 5, I open, try to 30 close, looks fine to me. Inputs PNM, okay, why not? 2 outputs Sansa, okay. N0, 0. wait, so the part of n0, the initial state should be then ac, not 0, right? Because you're naming them in here. So it should be ac, not 0. And P9, this is the number of transitions since these are complete. Yeah, no. It's actually 10 because it's a complete FSM with 5 states, 2 inputs. It should be for a fact 10. Yeah. And then you should list all the 10 transitions. Let's see. Ac M to try to sun. Yeah. For example, I don't see ac with plus. Yeah, don't worry. It's also very tricky of a format. I know. I always said to myself that we should, generate from a canvas this kind of format, but I never did it. Sorry. Someone should do it at some point. All right. It seems that you're getting it, and I need to finish in some minutes. Let me actually show you what I got myself, and so this would be what I would consider the FSM. Okay, this is the FSM described in that format, and let's use the tool. So I'm sharing my screen right now. So this tool, you select your file, and so in here I conveniently have it already, very close to me. If I open this FSM, then I can choose different testing methods as well. And we were talking about different ones, right? But we will just simply do W, for example. And so once you choose W, of course, you need to choose an upper bound in the number of implementation states. For, for intended purposes, we will say that, these implementations cannot increase the number of states, so it's the same number of states. And we will generate the test then. And as you can see by magic, you have all the test sequences in here, which is very convenient. You don't need to make the crazy huge tree, or you don't need to, add all the preambles and so on. So actually you can use these tools to generate different methods, right? If you want as well, you can do something more basic. You can do a transition tour. And the transition tour, as we said, it was way simpler, but of course, it does not detect all types of faults. So that's the downside of it. And so, well, you can use this tool actually to generate your test cases. There are other options that the tool actually allows you, other generation methods, but as you wish, anything is fine in here. Now let me return real quick to the end of this presentation. Let's see, where are we? Yes, we're here. Okay, so yeah, I will share the slides with you so that you have all the information in there. And if you have any questions, this is the right moment to make them. If not, anything that you feel like asking about, or you want to know more, or you feel like collaborating, or you want to do anything, you have our contacts in there.